Yeah, thank you. Yeah, I think my screen is visible. So we will make a couple of more minutes and then we'll get started. In the meantime, let me introduce myself. So these sessions are, so I'm Durga Prasad. So I'm a PhD scholar at IIT Madras, and my research area essentially involves it involves convective heat transfer as applied in the domain of building energy systems. So for this particular course, these sessions are aimed to help you solve your assignment problems. And if you have any queries during the lecture videos, you can raise those queries in this particular session. You can also, of course, obviously put them in the discussion forum, but a different TA will be addressing them in the discussion forum. You can also ask the question same if you have any problems related to the assignments or something, you can raise them in this particular session. Uh, we have around 6 students, or maybe we'll wait a couple of more minutes. If few more students will get joined, or then we'll get started. So, but before that, if you want, you can introduce yourself. I just want to know maybe you can put it in chat box if you're comfortable in that way. So just your background as in UG or PG, and then your department will be sufficient, like if you're from mechanical, chemical, or which branch you are. And if you are from industry or something, you can point that out as well. I guess most of you are. Just wanted to know, like, have you already gone through the lecture videos before joining this session? You have gone through the lecture videos. Yes. So basically, in this one first week, there is not much problems that I could discuss. So I just want to kind of give you a brief intro over it, and then I think we might end the session way before 7 o'clock today. But from next week onwards, maybe I'll try to put some problems you can solve. Or if you have any queries, we can discuss them as well. Okay, I think I'll get started. So do you have any specific questions that you want to ask before I'm getting started? Or you want to introduce yourself or something? That is also fine. Oh, so you're from mechanical, right? So you are in your which year? So you are in which year? Oh, you have joined recently. So this is your kind of a first course for a, like you have done fluid flow or incompressible flow before in your undergrad. You have not taken a fluid course before. Okay. CFD. Okay. And to give a brief overview, then this particular course is mainly on convection mode of heat transfer. So I kind of expect you to have a little understanding of incompressible flow. It is the governing equations, the Navier-Stokes equations, and how do we kind of formulate different kinds of boundary conditions. Those are the kind of concepts that you might know, but otherwise I can kind of give you a brief overview before. If you are not familiar with them, then you can just let me know so I can kind of give a brief overview before discussing those concepts. Towards the end of the course, we'll also discuss free convection and turbulent flows. And before concluding the course, we'll also discuss a little on boiling as well. As I said, the intended audience are PG or UG students or mechanical or any similar branches as long as convection is under their domain. And prerequisites is you should be familiar with a little bit of differential equations, and like you don't need to solve them completely, but at least if you have an idea of how to read an equation and formulate your own problem in terms of differential equation, that should be sufficient. And heat conduction, though not completely necessary, but knowing Fourier's law, and if you have solved some problems before, that should be enough for this. Fluid mechanics, I kind of expect you to have a basic understanding of what incompressible flow equations are, the Navier-Stokes equations, the continuity and the momentum equations. we won't be deriving them in this particular course. We'll be taking that you already know these equations and we'll build on from there. So if you are not familiar with them, maybe you can brush up on those before, or if you want, I can take, just let me know before so that in the next class or something, we can have it in the say first half an hour or so. I can give you a brief overview of what is necessary for this part, for the problems that are given in your assignments. That particular part, I can kind of take it out and describe if you are not familiar with that. And books and references, I'll be following the last reference here, Patient's convective heat transfer, but you can choose whichever one you want. It's up to you. And the professor won't be joining these sessions, but if you have anything in particular that you want to discuss with him or something, you can put it in the discussion forum, which he will be having access to. So he'll also go through that. Or if you have anything that you want me to ask, you can just let me know in the session itself, so I can also convey that to him. And anyways, you have the mail ID of him. You can send it through the discussion board, through the NPTEL link, which will be reaching. And about myself, as I said before, I'm a PhD scholar at IIT Madras. I'm in my 4th year. You can also reach me out through my email, the same one here that I've used to join this session. I'll also share a link for this particular website so you can go through all these sessions. And these slides will be updated after the session we are having here. Now coming to the first week lectures, it's mostly kind of an introduction one. So we'll discuss what basically a transport phenomenon is, what are the types of things that we'll be discussing in transport phenomena, and some general applications of heat transfer, different kinds of different modes of heat transfer, and why we need fluid flow equations and what are the different types of flows that we will be dealing with. And finally, we'll be concluding this particular session on just stating what the continuity momentum equations are. And a few problems I have, which I would like you to solve yourself. Maybe you can unmute yourself and kind of, these are kind of an objective questions, so it won't be taking much long. If you want to go through them before, I can share you the link. So you can go to this site and you can find the questions yourself so that you can, when I ask, you can kind of tell them immediately. Yeah. So starting out with the transport phenomena, it's basically, in general, we say some physical quantity is being given by a force so that it moves from a particular point to another point. So, but the type of questions that we will be answering in this particular course are, what are the quantities that can be transported? There are some quantities that can be transported and some that do not. So what are things that were transported, and out of these, what are the quantities that we will be studying in this course? And when you say something is transported and we are measuring it, the next obvious question is how much is being transported? What is the rate at which it is being transported? And how do we alter the rate of transfer as per our objectives depending on case-to-case basis? These are the types of questions that we'll be answering in this particular course. And most importantly, this is the last question, is what we will be interested in from an engineering point of view. So this is a simple one where you have a boiling kettle or something. So heat energy is being transferred here. So you can see this is a kind of a transport phenomenon. The quantity that is being transported here is a heat energy from the flames to the ambient eventually, carried by the gas molecules that are present here. This is just one example. You can find several examples outside. Major applications broadly, either you see from a natural point of view, which are already existing, like climate change, or generation of dew and fog, heating and cooling effect. All these examples are already given in the videos. I hope you have already gone through it, so I don't want to spend much time on this. And then you also have industrial applications where you have heat exchangers. If you're already familiar with heat exchangers, it's good. Otherwise, it's basically you want heat transfer to happen between two fluids, and this heat transfer is going to happen inside inside an appliance. That instrument is what we are calling an heat exchanger. We wouldn't call it an instrument, but let's say that particular device is what we are calling a heat exchanger. And it finds applications in different places for cooling or any heating application or any cooling application where you have very high heat fluxes. The normal way where convection alone won't be sufficient, we might have to have a fluid flow, and that's where convection comes into picture. We find it in manufacturing, automobiles, aircrafts, power plants, electronics, cooling, everywhere. Anywhere you can think of where you need cooling at very high densities, we will be using convective heat transfer. This kind of a quick question to just understand how conversant you are with this particular topic. So we say a transport phenomenon. So which of these quantities do you think can be transported? So all of them are physical quantities. So we define that transport phenomenon is basically transport of some physical quantity. So which of these quantities do you think can be transported, and which of these cannot be transported? Mass. Temperature, pressure. So you think these things can be transported? Okay, so you think density cannot be transported. So like, do you have any kind of a, like, how do you assess whether some particular quantities can be transported or not? Like, you can just say what your way of thinking is. There are another students who have any other thing. You can also kind of, you can unmute or just put it in the chat box, whichever way you are convenient. I just wanted to be interactive so that we can discuss more. So first of all, even before dealing with, I think you are familiar with all these quantities, right? There is no doubt in any of what these quantities are. Mass, density, velocity are straightforward. Momentum is straightforward. Enthalpy you are familiar with already from thermodynamics, I guess. Enthalpy and entropy. Yeah, enthalpy and entropy also okay. So what is the criteria that you are using to kind of decide which can be transported or which cannot be? Is it completely based on intuition or you have any other reason to say? Yeah. So what is being transferred when there is a temperature difference? So what is being transferred when there is a temperature difference? You are saying heat is being transferred when there is a temperature difference. So what is being transported there? Yeah. So heat is transferred or is temperature transferred? Yeah. So temperature is something that is not being transported, right? So it is the heat energy that is being transported. So temperature is not transported. So is the pressure transported? Yeah, so basically, you are kind of if some quantity is being transported, then it has to be associated with some material or some matter has to be moved from some place to another place. And as the matter moves, whatever is thing that is moving with the matter is what we are calling that particular quantity to be transported. So if that is the case, what about density? Is density being transported? Okay, so why is it not? Yeah, okay, you went on a different one. Okay, buoyancy force. Let's say, but it is a force thing. So buoyancy force, okay, good. So you mean force is something that can be transported? Okay, even before that, let me ask you in a simple way. So does it mean that whatever quantities that you have given here, all are scalars, right? Mass is a scalar, enthalpy is a scalar, entropy is a scalar. So all these are scalar quantities. So does it mean that vector quantities can't be transported? I mean, I have both scalars and vectors listed here. And as of now, out of the pointed ones, so all of them are scalars. So like say velocity, momentum, force, these are vectors. So does it mean vectors can't be transported? I think you were kind of in the right track when you were saying that matter has to flow from somewhere to somewhere. So it has to be something that is associated with matter. Till that it was clear. So what makes the difference between like why is density not there that can be transported? What is it that is preventing density from being a quantity? Like why do we have to care about like before even going into the equations, you need to know why which quantities can be transported or not. Because once we know that when we derive conservation equations or some governing laws or something, these laws are kind of based on, at least the ones that we'll be going to discuss in this particular course are all based on the transport quantities only. whichever quantities can be transported, we'll be able to write some laws. Their laws are something like, you say some quantities transported some from some particular A to some particular B, then we will write some conservation equations on them, which we will see later, where conservation is based on some kind of conservation will be there. So for example, if mass is there, we know that mass can neither be created nor be destroyed under the normal conditions. So from that, we will say that, okay, if at some particular point A, if mass has decreased, it means it has moved out of A to somewhere else B. So if, because mass can be transported, we can kind of write some equations like that. So it is kind of important to know which can be transported or which cannot be transported, without which the equations do not have meaning as such. So I would kind of encourage you, if you can think a little more, like you are on the right track, you can maybe what is a more better criteria. So is velocity transport quantity? Density, I think you are correct. Like your line of thought was correct. So basically, the way you define density is mass per unit volume. So in order for the quantity to be defined, you need the spatial volume to be fixed. So during transport, the definition itself is not valid. So density can be ruled out. But what about velocity or say momentum or pressure, force, or power? We have a lot of more other options as well. Hmm. Yes. Yeah, so that is one criteria. So basically, you have something which drives and something which is driven by something else. The transport quantities are something that are driven, and this density and etc. are the things that are driving these changes. Yeah, so okay, if you put it in that way, so just that you since that you pointed out, so if mass is something that is driven, what is the driving force for mass to be transported? Okay, so you are saying if there is a force and there will be a change in mass. I mean, if you put it in that particular framework where you have a driving force and then there is a driven quantity. So whenever there is a force, something has to change. That is the driven quantity. So what will change when you have a force? Yeah, you are in the right track. But if you want to be more precise, what is it that will change when you apply a force? Is it just the position or is it something else? Like from Newton's second law, what do we have? Yeah, or you put it in another way, it will be basically the rate of change of momentum, right? So when you have a force, it's a momentum that will be changing. So momentum is a quantity that is being driven. So that is the quantity that is being transported under the influence of force. So momentum is also a transport quantity if you put in your framework. So in a similar way, what about enthalpy and entropy? What do you think these things are? Okay, let's even before that. What about temperature? I think you already said this before, right? When you have temperature difference, that is giving heat energy. So the heat energy is what that is being transported, and temperature difference is just the driving force. The same, if you're already familiar with the concept of enthalpy, you might already be knowing that delta H, M times delta H will give you the net heat energy that is transferred. So this is kind of equivalent to, you can relate it with heat energy. So this is a quantity that is being transported, just like heat. It's just a way to measure the amount of heat transported. The same applies for entropy. Again, pressure is also the same. So pressure is will drive, but it is not being given. Force is also the same thing, and power is also the same. So I think it is clear. Are there any questions? So now you have seen these things. So these are the quantities that we will be writing equations for later. So you'll have one equation for mass, we'll have one equation for momentum, and instead of enthalpy, we'll say, let's say energy equation. We'll have one conservation equation for energy, and we'll also I'm not sure if we'll be using this thing, but we also have one inequality for entropy also. These will be the four conservative equations we'll have. Entropy as such is not conserved, but we can have an equation for it as well in terms of an inequality. Sorry, I would call it an inequality, but we have one inequality for entropy. Now coming to heat transfer, that is the main objective of this particular course, which you're already familiar with, so I don't want to go much into it. So you have three modes of heat transfer: conduction, convection, and radiation. The basic laws governing these are: for conduction, we use the Fourier's law, where the heat flux is given by K times grad minus K times grad T, where grad T is the gradient of temperature field inside that particular domain, K is the thermal conductivity of the material. Ideally, this K should also be inside this. I've assumed that the properties are uniform and constant. And for convection, we have Newton's law, where you have heat flux related to the temperature difference between the surface and the ambient by a proportionality constant H. But this H is not a constant, universal constant or a material property. It is something that depends on both the material geometry, the type of material, the type of fluid, way in which the fluid flows, and a lot of other factors. That is where the complexity comes, and that is why you need to know the fluid flow as well. Just knowing the properties of the material won't be sufficient to kind of completely quantify the amount of heat transfer from a convection phenomena, and that's where this particular course. That's why we need to have a little background of what the fluid dynamics is. And comes the radiation, where we do not require any material medium, but this is kind of not discussed in this particular course. And as you already familiar with, in general, in practice, in all scenarios, we have all the three types of heat transfer happening simultaneously. It's not like you have pure conduction or pure convection or pure radiation. All three of them will be present, but the relative strengths of them will be different. So for example, if out of 100 watts, maybe conduction is 10 watts and convection is 98 watts, 88 watts, and the remaining 2 watts might be radiation. So we have to kind of come up with a criteria which tells us what is the relative strength of these, so we can kind of make reasonable assumptions and be certain about what is the error that is associated with whatever we are estimating from using these equations. And I hope you're already familiar with the difference between convection and conduction. Just as the terminology goes, convection is basically conduction plus advection. The major difference between these two phenomena lies in, again, as you said before, it's on the driving force and what is being driven. In conduction, it's basically a diffusion process where the particles do not have any preferential direction of movement, which means it's completely random. They move in all directions, but just because the relative concentrations are different on in different spaces, where the concentration is higher, we tend to see that the direction moves from higher to lower, but in reality, it is completely random. But when it comes to advection, it is an active process where the particles will have a preferential direction, and this preferential direction can be imposed either by us through external means, or it can be because of the buoyancy forces, like you said before, in case of natural convection, or if it is a forced convection, it will be induced by us in whatever conditions we want it to be. But again, both of these exist simultaneously. It's not like something is purely natural or purely forced or something like that. We have everything always, but the relative strengths will be different, and we have to come up with a way to kind of assess these relative strengths in some way that we will be discussing later. As I said, the flow structure is important when you deal with convection because it is an active transport. So unless we know what how the energy carriers are moving, we do not know where the energy is being transported to. So we need to have a basic idea of what the different types of flows are. So in general, broadly, we have either external or internal flows where you have the fluid moving. The another idea is once we introduce the concept of boundary layers, this will be more strongly, it will be much better to understand. Why do we have to know whether it's an external or internal flow? To put simply, you can kind of think when there is a confinement and the effect of confinement on the flow is significant, then you can call it as an internal flow. And when the effect of external confinements is not there and it's the only surface that is influencing, then you can consider it as an external flow. It's like an unbounded and a bounded thing. And then we have, again, from a heat transfer point of view, we have forced, mixed, and natural convection flows. It's again, as I said before, in forced, you are kind of giving energy to drive the flow. In natural, the energy is being given by you sometimes directly, sometimes indirectly, but it's majorly the body forces, which is basically the buoyancy force that will be driving the flow. But in general, we have both the buoyancy as well as force acting simultaneously. So that is a case where you have mixed, but depending on the relative strength, you decide whether it is the force. If the relative strength is way higher, then you just the force you are giving is way higher compared to the buoyancy forces, and you will consider it force. Otherwise, it is natural. And when they're both are comparable, then you would be calling it a mixed convection. This is a kind of a sample animation to just show you. So like consider this is a chimney and some particles are moving out of it, like the hot air moving out of the chimney. So if the particles are moving something like this, what you can see is the buoyancy force that is dominating here. So this is kind of a pure natural convection case. But of course, if some wind flows over the chimney, then this particular smoke will actually bend towards one side. So as it keeps bending, you can see the forces acting on it will keep changing. So the strength of the buoyancy force will gradually decrease as you keep on increasing the wind speed. If the wind speed is way too higher, then the particle will just follow along the wind path. So there will be a portion of region where you have the natural convection being dominant, because there the wind forces are comparatively smaller compared to the buoyancy forces. And there are again regions where the wind force is much higher compared to the buoyancy forces. So you can have flows where part of the regime will actually be forced and other part can be natural convection as well. So it's not like entire flow will be forced or entire flow will be natural or something like that. So you can have mixed, uh, you can have different regions having different kinds of flows. The same applies for external and internal flows. So you can have a big domain where you have certain regions treated as external flows and certain regions treated as internal flows. So I want you to kind of understand that it is the relative strength of these forces that is important than just seeing the whole configuration and saying something. Like on a global picture, sometimes these local things also matters. And incompressible flow equations, I do not want to go into the derivations. I hope you are already familiar with them. I just present the equations here. So again, for an unsteady, incompressible, Newtonian and constant property fluids, we have the continuity equation in the vector form as divergence of p equal to 0, and then the momentum is, you have different terms in this, which I hope you're already familiar with. Otherwise also, so this is basically what we have an unsteady term, and I call this the advection term. So then this is basically the net force, which is balanced by your viscous forces, body forces, and then the pressure forces, hydrostatic forces. If you want to write it in the Cartesian coordinate system, so these are the equations you have. And the most interesting thing here is in incompressible flows. For these particular equations, though I stated that you have constant properties throughout, that is an assumption we have taken. So that is one reason why you do not have any unsteady term in the continuity equation, but that is not always the case. You can still have variable properties like, as you said in the natural convection, for example. When you take a natural convection example, density is a property that will be continuously varying, because I mean otherwise there is no natural convection or the buoyancy forces. So when you have a hot air inside a room, say for example you're sitting in a room and then you light a matchstick or candle or something, then you have plumes, or basically you have some the air reduces the density and it keeps moving. In those cases, density is not constant, but still we can use this assumption of incompressible flow as long as the velocities inside the particular flow are very less. The exact requirements as to that depends on the Mach number of flow. You can refer to this textbook if you're interested in that. But for this particular course, we can initially restrict ourselves to incompressible flow, where you can assume that density is more or less constant. As I said, these are the different names. I just want to be familiar with these terms so that I'll be using these terms in the problems also. So the time derivative term, I'm calling it unsteady term, and this u dot del v is what I'm calling advection term. Pressure term is basically the gradient of pressure. Viscous term is what is multiplied with the viscosity, and then you have the gravity term. You call it either gravity or body force. Now that we have the governing equations, the next obvious thing is we have to know the boundary conditions. Only when you have both of them, you'll be able to solve these particular equations. So broadly three kinds. You have a Dirichlet condition where you actually specify what these values are at the boundaries. Neumann is where you specify the gradient of these conditions, in which this kind of you have it's like giving a heat transfer coefficient, which means you will have both the gradient and the value in an equation in a coupled way. Just to be clear, so how many variables do I have in this, and like is this problem solvable? So I have four equations here, and I have I need to know the velocity, I need to know the pressure, I need to know, for example, density and viscosity. So I have like four unknowns, and then I have only two equations, the continuity and momentum equation. So will I be able to solve these equations, or maybe I should show the previous one? Yeah, I'm doing this. So I have two equations, and I have how many unknowns? I do not know the velocity, I do not know the pressure. So it is two equations and two unknowns. Provided we know the values of density and viscosity and the acceleration due to gravity, all other values being known, it is two equation, two unknown. But it is not actually quite straightforward to solve these particular equations, because the pressure comes only in one of these equations instead of two. So we'll see this problem later. Maybe once one of you have mentioned that you'll be taking CFA course, so you might actually come across this later. The challenges on how to solve this problem, because one of the variables applies comes in only one equation but not in both the equations. Yeah, so it's kind of a brief summary of what is in this course. If you have any questions that you want me to, that you have to ask. Okay. Then I would like you to solve these problems. Maybe I'll wait for maybe I'll give you 5 minutes or something. You can quickly solve these problems. Just make sure that you kind of familiar with the concept. There is any thing that you need clarification in the question, you can just ask. Hope the question is clear. This is more on if you're already familiar with the resistance method to solve this, then it would be straightforward. I hope you have done this in your heat transfer course. If not, then maybe I have to explain you that before. Are you familiar with solving these kind of problems before? Since this is a first class, I do not know the background of all the students. So let me know if you have any challenge with this, or if you're already familiar with it, you can just solve it. I think you would have solved it by now. So what do you sounds? Can one of you tell me how you solved it? So only 166.7 milliwatt per meter Kelvin. Yeah, you can kind of like, I would prefer to have the procedure as well, like instead of just the answer. So I've given a range of values. You can kind of tell me how did you choose the value. So did you take? I want to kind of find the maximum, sorry, the minimum value of thermal conductivity. So which value of H did you choose, minimum or maximum? And which value of the ambient temperature did you choose, minimum or maximum, and why? Like you have range of values for ambient temperature and range of values for heat transfer coefficient. So in order to calculate the conductivity, how did you choose? How did you go about choosing the correct value, and what's the procedure for it? Okay, one of you have text, kept a message in the chat box. So how about others? Okay, I'll share my screen. This is the kind of problem we have. So if you are familiar with the resistor method, or if you just write the conservation equations for here, the net heat transfer from the base of the plate should go through the particular material through conduction. Like this is particular insulator that we have. So it go through the insulator through conduction, and from the insulator to the outside ambient, it will be going through convection. So assuming it to be steady process, the net heat transfer from here should be equal to the conductive heat transfer, which is K times delta T, like Tc minus Ts by the thickness, which is 5 mm. And this should be equal to the amount of heat transfer due to convection, that is H times whatever the surface temperature minus the ambient temperature, let's say the T infinite. And we are interested in finding this K. Given that Ts cannot exceed 150, let's say Ts is 150, this is the worst possible condition. Then what is the value of H that you have used for this? Like, how did you go about solving this? So I know T, I know H, I know T infinity, but I only know the range of values of T infinity. Again, for H also, I only know the range of values of H. I do not know the correct value of H. But you can just pick one value, either minimum or maximum, one of these. So I have, I know Q double prime. So I have 6 variables, out of which I have one equation here. Sorry, basically 2 equations here, 3, 4, 5, 6. Like each of these tick marks basically gives me the value of that particular quantity. So this will be 1. If this is first equation, this is second equation, and then I have 3. So I have 6 variables and 6 equations. So this is a problem that we can solve. All we need to do is formulate it correctly. So we'll be getting an answer. Yeah. So how did you go about picking the values of H and this T infinity and stuff? Okay, you have chosen H equal to 10 because when you want the maximum temperature of TC, so basically we don't want the material to have, basically from material constraints or something, maybe the material is unstable beyond a particular temperature, so that will be kind of a limitation that will be given by your material engineer. So it says that, or from the catalog we found that 150 Celsius is a maximum temperature that you can go to. So the temperature here cannot exceed 150. So we know that Tc or Ts, whatever, the maximum temperature here will be on the side where it is facing the heat. So this will be the maximum temperature that will be happening. So this should be less than or equal to 150. If this is less than or equal to 150, what should be the value of, let's start from here. So Q double prime is H times Ts minus T. What about T infinite? Which one have you chosen? Once I fix the value of T infinite here, I can get the value of Ts, which I can substitute back here and can get the value of K. So basically K is Q double prime T plus. So once I know the value of this, I will be able to do T infinity is 20. You have chosen the minimum value for T infinite. Okay. So do you have any reason for choosing that? Like for both of these values, you have taken the minimum values for H, minimum H and minimum T infinity. Any specific reason you have for choosing them? Or you have tried all the combinations? For minimum required conductivity, I want K to be minimum. Okay, let me write this equation in terms of K, then that will be straightforward. Yeah, I want K to be minimum. So what would I want by Tc is kind of fixed. So I want the Ts to be, so I want K to be minimized, and it is inversely, it is directly related with Ts. If Ts increases, then the difference will decrease and K will increase. So if I want the thermal conductivity to decrease, that is, I wanted to get the minimum value of K that I can use, which means I want my Ts to be increased, Ts to be decreased. If I want my Ts to be minimum for a given heat flux, what should be the value of H and T infinity that you require? Like, is that how you kind of came up with these values, or is there any other reason? These sessions are kind of meant to be interactive, so I don't want to kind of give away. I mean, I don't want to just keep solving the problem or something. I want you to kind of solve the problem yourself. And while solving, if you face any problem, then it would be better if we can discuss them. So that way, it will be more useful for the students as well. And I think I kind of didn't mention before, but all these sessions will be recorded and will be uploaded on YouTube. So you can, and you will also be given the link to these particular recorded videos in your course webpage itself. So you can, if you are not able to attend this particular session for some reason, you can access them on the YouTube as well. So for you to really benefit from the session, I would kind of prefer if you can kind of solve the problems during the session itself and tell me where you are facing challenges so we can have a discussion and then solve them. Yeah, coming back to the problem. So I know Q double prime. So I wanted, what we wanted to find is we wanted to find the thermal conductivity that will kind of you were trying to say something. Okay, let's just assume, for suppose, let's just start with the one that is already given in the chart. So if you have taken H equal to 10 and T infinity equals 20, what would be the value of Ts you will be getting? So this is the equation for Ts. And from this relation, we know that when I want to minimize K, I want to minimize Ts. And if I want to minimize Ts, Yeah, so your T infinity should be minimized and your H should be maximized. So if you take those values, so basically it will be 1000 by, I want H to be maximized and T infinity to be minimized. So that would give me around 70 Celsius or something. And from there you would get K equals, it is in milliwatt, so I don't have to convert it into meter, by 150 minus 70. That is around 62.5 or something. I think you gave a different answer before. Is this clear or are there any questions? Okay, let me just do with the other one as well. Let's say you have taken H equal this particular case, and let's say this is case 1. Case 2 is you have taken H equals to 20 and T infinity equals 20. Let me take the other value where, let's say, for the first case, what is the value of K you are getting? If H equals to 10 and T infinity equals to 20, that will be getting around 166.67. For the second case, we got around 62.5. What is the other possibility that we have is we can take H equals 10 and T infinity equals 30. So what would be the value of K in this particular case? We can quickly calculate it, I guess. I'm getting this around 50 or so. Sorry. Is it visible now? Okay. Yeah, so I think this is the value you're getting. If you try other combinations, you can try other combinations as well, but the logic goes in the same way. So you want to find the minimum thermal conductivity, so you have to minimize this particular TS. When you want to minimize this particular TS, you have to use the value of T infinity that is minimum and then the H that is maximum. So that's straightforward. Moving on to the next problem. So this is again something that you might have already come through lecture videos, just to kind of a testing. So if you have radiation and you want to kind of approximate it using a heat transfer coefficient, what would be the heat transfer coefficient? So if you want to write a radiation equation, but then still you want to use the Newton's form, kind of Newton's form, how would I write it? So we know the radiation equation as something like Q double prime is T power 4 minus T naught power 4, but I still wanted it to use Newton's form. So basically I want to write something like H times T minus T naught. So what would H be? And basically, so obviously if this is the case, H will again be a function of this temperature, H will be a function of epsilon sigma and all this stuff. So what would it be, and where we can kind of make such approximations? I'll give you a couple of minutes so you can quickly come up with an answer. I just wanted to know beforehand. So how many of you are already familiar with programming? Like if you want to write some, say, finite difference code or something. How many of you are already familiar with programming? Like we might have to, like depending on if you're familiar, I can kind of give some problems on using programming. If you are not, then we'll see something else. Or not familiar. Okay, fine. So you have not done any programming before, like you are not familiar with any language, like Python or also nothing. Okay, fine. Okay, no problem. But I think you have access to MATLAB or something. Yeah. Okay, so what do you think? Which of these is the answer? You can kind of just do an expansion that you're already familiar with. So this is basically a square, a power 4 minus b power 4. You can kind of expand it into t square plus t naught square, t plus t naught into t minus t naught. So when you multiply this, it will be t square minus t naught square, and then it will be t power 4 minus t naught power 4. Now, only under the cases where t and t naught are kind of very close. For example, when we consider scenarios like our normal room temperatures, where you have the temperature, actual temperature is say 300 Kelvin or let's say 310 Kelvin ambient temperature, and then let's say the room temperature is around 24 Celsius, is say 298 Kelvin. So under these conditions, you can roughly calculate these values. You can calculate what the value of this versus the 14 naught cube. You can do that if you want to. So if I just calculate that, and instead if you're just doing 14 naught cube, and you have sigma which is 10 to the power minus 8 or something. So up to the first two or one, like the error will be quite less, like it will be little less than 10% or something. So if you multiply this with sigma, which is again 5.67 into 10 power minus 8, so most of these terms will actually be going off, and you'll be left with only up into here, which is still kind of accurate enough. So for most engineering scenarios where you have the temperature difference between the ambient and that particular surface is kind of little less, or the temperature itself or very less, in those scenarios you can do this. But obviously when you have a hot furnace or something where the temperature itself is 500 Celsius or something, then it will be like 700 Kelvin and to 300 Kelvin. That difference is too huge, and this assumption will not be valid. So only under this moderate conditions, like 30-40 Celsius kind of scenarios, this particular approximation is valid, and we can still use this relation. So even though this fourth order power we cannot, we can simply replace it with this particular one. And since the ambient temperature is constant, this particular H that we are taking is constant again. It's like it doesn't depend on the ambient temperature. It only depends on the emissivity and other properties. Like, there is another view factor thing which I'm not discussing here because it's not relevant to this course, but we can just assume that this particular quantity to be HR times T minus T naught. So the net heat transfer from that particular surface will be the convective heat transfer coefficient plus the radiative heat transfer coefficient times the temperature difference. So this is especially useful when, say, for example, you want to kind of say you have a building wall that you want to analyze what is the heat transfer because of the solar radiation falling on the surface of the wall. The temperatures on the surface of, say, window or something. When you have a window glass and solar radiation is falling on the glass, and you want to find out what is the net heat transfer from this. In that particular case, you need to know what is the heat transfer happening on the outer surface of the window. There, you can kind of approximate it with this HR because the temperatures there will be like 40 to at max 40, 50 Celsius, depending on the kind of coatings you have on the surface of the glass. So in those particular scenarios, you can directly assume these values of HR. The values will be provided in tables. So you don't have to solve the complete radiation equations, and this should be fine to kind of calculate the net heat transfer on the outer surface of the glass plane. Is that clear? So this is the kind of to brush up your understanding on the Navier-Stokes equations. So if you need to take the Navier-Stokes equations, which of the following terms will be zero under hydrostatic conditions? So what are hydrostatic conditions? So if this is your Navier-Stokes equations, so which of these following terms will be, let's say, let's give some numbers so you can put in the chat box if you want. Which of these terms, like Navier-Stokes equations are valid? Let's assume that these equations are valid. Now I want to see which of these terms will be zero when you have a hydrostatic case. So you're saying 3 will be zero. Okay, and then actually hydrostatic doesn't mean pressure is constant. Basically, it's like let's say this scenario where you have a tank with some water in it. This is basically water. This is the free surface of that particular tank. So this is what we call hydrostatic case, right? You have the tank on your rooftop. The water in that tank is basically in a that is something like a hydrostatic case. So is the pressure constant throughout this particular thing? Like you are an open to atmosphere kind of thing. So is pressure constant in the water throughout? No? Okay. So what conditions do you think are valid in this particular scenario? Okay. So let's say what about velocity? What can I say about velocity? Will it change with time? Velocity is constant. What is the value of velocity? Difference between, like when you say difference, it is between two different points or something. So which point? So what about the actual velocity? Like not the difference, but the actual velocity. So okay, let's say when you say difference between which point and which point were you referring to? Yeah. So hydrostatic basically means in this particular fluid, velocity is zero. So which of these terms will go off? Your first, second, fourth, all these terms will go off because all of them are zero. Like all of them have velocity, so all of them will go off. The only equation will be remaining with this grad p equal to z. So in the one dimension, like in this kind of scenarios where you have only one thing, so you have, if I put my coordinate axis this as y, then del p by del y, g will be opposite direction, will be minus rho g, and if you integrate it, you get your hydrostatic case where p equal to rho g h kind of stuff. This is a hydrostatic case. And basically, I just want to show that you just need to know what terms you are considering. So this is again. Now let's say if you have a scenario where you have a hole, that is where I think your velocity difference is coming. If you have a hole here, then a flow happens. Then there will be certain velocity in different region. There you get your torsion equation and other stuff, right? So all those equations again, you have to come up with the criteria. This keeps coming again and again in the course. So you start with the Navier-Stokes equations. Then depending on the problem you are solving, you need to identify which of these terms are important and which are not. Depending on your particular problem, you need to kind of, some terms are more important than the other terms. So that is what we will do later, called scaling analysis. We'll identify how these terms compare with the other terms and then reduce it, because this equation itself is too complex to solve. We'll kind of come up with a reduced form, simpler form, and then solve those equations. So basically here you don't have unsteady term. We don't have an inertia term because the velocity is zero. Viscosity is not there because the velocity is zero. Yeah, I think you're all familiar with this Bernoulli equation. I just want to make sure that this is again something we'll use again. This Bernoulli equation is also something that will come in your next week. So I just want to know if you're familiar with the assumptions under which this particular equation is valid. Can I use this equation in case of an unsteady flow? Or when you take the Navier-Stokes equation, just like before, in this equation, if I want to derive Bernoulli equation from this Navier-Stokes equation, which of these terms would be neglected? Even before that, I'm not sure if how many of you are familiar with vector calculus, like you have done something in vector calculus, you're familiar with these notations, right? This del and all this stuff. I think you have done this in your undergrad. This is the Laplacian operator, and then this is the gradient operator. You are familiar with the identities as well, so I can rewrite this in some other way. So let's say if I ask you to find what is the gradient of say u square, will you be able to expand it? Yeah, of course you can. Anyway, now ask GPT or something and you will get the equation. Like if I want to relate this with say, you can take this as an exercise. You can just review the vector calculus identities and then see how these two quantities are related and how I can kind of write this equation in a form slightly different. So if I write it in a form where you have this will come something like this, p will come on the other side. The g bar I'll write it as gy, and then you have the u square term that I was referring to before. Like all these terms will be zero. So if when you have a steady flow, this particular one, when you have a steady flow, and then when you do not have any viscous forces, under those conditions, when 1 and 4 are zero, in that particular scenario, these two terms will go off, and you will be left with this particular term. So you have the pressure term, you'll have the body force term, and then you'll have the kinetic energy term. And this particular thing you are saying is to be zero. So del dot something is zero. The gradient of something is zero, which means the particular quantity inside this operator is a constant. That is how you get your Bernoulli equation. So the assumptions are you need to have it to be a steady flow. You need to have, you should not have any viscosity. In those scenarios, you can kind of use this Bernoulli equation. And again, there is another important one that I didn't write it here. It's an irrotational flow. Like you need the flow to be irrotational. That again comes when you kind of derive the Bernoulli's equation from the Navier-Stokes equation, you will get the irrotational condition as well. Basically, what we mean by irrotational is the omega, which is del cross V. This particular quantity also has to be zero. If it is zero, then you can use Bernoulli's equation throughout the domain. If this is not zero, then it is kind of limited. You can apply it only along a specific line, which I do not want to go into. But the whole point is you can derive this from the Navier-Stokes equation. That is the whole point I want to make convey here. This clear or there is any question? I think there is no question. You're already familiar with potential flow. What are the conditions under which potential flow happens? These are kind of straightforward questions from incompressible flow. You can kind of brush up your concepts on incompressible flow again. So you need to have it to be an inviscid, basically where the flow does not have, the fluid can have viscosity. Inviscid is where the flow does not have any viscous terms in it. So in the Navier-Stokes equation, your Laplacian term, basically the equation above this particular term, fourth term is zero, then you call it an inviscid flow. And then incompressible, as I said before, is your continuity equation. You say del dot u equal to zero, then that particular flow is incompressible. And irrotational, as I said just now, so this particular omega that you are having here, if this is zero, then you call it to be irrotational flow. And now coming back on the different kinds of flows, as I said before, so when we have say forced or free or mixed convection kind of thing, we need to come up with a criteria that will help us identify which design we are in. And these are different kinds of non-dimensional numbers that we'll be using throughout the course that will help us identify which design we are in. And that is important because if you do not know the design, the phenomenon itself is completely different. Like forced convection, the driving forces are different, and in free convection you have buoyancy, which is completely different from forced convection. So unless we know the regime we are in, we will not be able to solve it completely. Like we have specific solutions to tackle specific problems. So the numbers here are, the first one is something called a Reynolds number, which is depends on some characteristic velocity times length or viscosity, and this is something we call the Grashof number, and then this is something called Richardson number. So which of these do you think will help us identify whether some particular flow is mixed or not? You don't have to know what the number is, but this quantity should be sufficient to tell whether it will be able to help or not. So this is velocity, length, and viscosity. G is acceleration due to gravity. Beta is the volumetric expansion coefficient. Delta T is the temperature difference. L is some characteristic length, and this is viscosity of that particular fluid. The same definitions go here. Which one is Rayleigh's number here? 1, 2, or 3? So the last option is what should be mixed convection. Cool. So you can kind of tell it from the equation itself. So if when you want to decide whether it is mixed or not, so basically it's a compromise between the buoyancy forces and something to do with inertial forces. So it has to have the gravity and it also need to have something related with velocity. Only when you have these two, that particular parameter or that particular quantity can be used to classify whether a flow is mixed or not. And only this particular non-dimensional number has both in it. Here you do not have velocity, here you do not have gravity, so these two cannot be directly used. Yeah, so these are the questions I have for this week. Do you have anything specific that you want to ask? Or this is the first class, so I don't think it will be till 7 we would require all the session. So if anything in particular, we can discuss that. Right. Do you have any feedback? Like this is the first time I'm taking this particular course as a TA, so if you have any feedback, feel free to tell me now, or you can put it in the feedback form that will be shared with you later by the NPTEL team. I'll go and have access to it, but it will be better if you can kind of tell me now. So either the format in which I teach, either now currently I just want to do it in the same way. Like I will take up a summary followed by any questions you have. If you do not have any questions, then I'll pick up some problems and then we'll discuss them. If there are no further questions, then I think we can call it a day for this particular week. Okay, then we'll end the session for this week and we'll meet next week. Thank you for joining.